thank you very much for the Jug Amsterdam, for the spot. I know how much it's difficult to organize meetups and events, so thank you. The microphone, sorry. Can you give me the microphone? Maybe it's better. Okay. It's better? Yeah. Thank you. Okay. So I was saying thank you for the JAG Amsterdam, for the occasion, for the spot. And yes, I know how much it's difficult to organize events and meetups, so thank you again. So I have a few times, so I'll go very fast on the next slide. So I'm Giovanni, I'm software engineer at IBM, but the most important thing is that I'm the Visium core contributor. Apart from that, I'm also Zig Zig OpenTelemetry SDK contributor, and also Ticino Software Craft meetup organizer. In this photo, you can see me in my natural form drinking some beer. Okay, so after this embarrassing moment, let's jump to the main topic. Okay, before jumping to some practices, so let's talk about a bit of theory, okay? Change data capture is a data integration pattern, okay? We have many data integration patterns, but change data capture is a data integration pattern in which you have you migrate data from a system to another in a particular form, in the form of insert, update, and deletes. So you are thinking about SQL database, yes, but today change data capture is a pattern also for NoSQL database, and now with AI also for vector databases. The use cases are multiple. The most important one, the most famous one is data synchronization. For example, yeah, it's much better because, yeah, okay, sorry.
It's just the support's a bit low.
Okay. Okay, so, more minutes, eh? Okay, so, I'm not so, okay. So, for example, the most famous one is data synchronization. So, for example, we have, like, you know, a data source, a database, a data source, in which we want to align another system in near real time. Well, CDC is the right pattern for you. Or, for example, for event-driven architecture. For example, you have your data source, your database, and you want to react to the changes from the database and trigger some business process. Yes, change data capture is the right pattern for you. Or, for example, if you have you want to create some read view from different databases and data sources, again. Or last but not least, audit trails. In your organization, for example, we are in Europe for GDPR, you want to monitor all the data sources for data compliance, you can do it with the change data capture. And in this context, yes, in this context, the Visium is an open source distributed platform for change data capture. The idea of the Visium is to stream real-time changes from databases to event-driven system by monitoring the database transaction log. Well, this point is really important because you can implement CDC in different way, but the transaction log is the way that we use in the Visium. I don't have enough time to talk you about the trade-off, but trust me, it's the most efficient way to take data from a data source. And obviously, if someone of you know the Visium and Kafka, the Visium from the version 0.1 is live inside the Kafka runtime. The Kafka runtime, Kafka Connect runtime is Kafka Connect runtime is built on top the Kafka API, and Kafka Connect permits to the Visium, well, is responsible to handle the entire life cycle of the Visium and also scalability, availability. The Visium, from its part, is responsible to know how read data from a database. Obviously from the transaction log. But today the things are a little bit different. We offer, in the Visium, offer a different way to solve CDC in different contexts. as I said before, we have the connector, which are the oldest part in the Bizium. But today we have also the engine, which, I mean, I think that some of you know Apache Flink. Inside Apache Flink, there is the Bizium engine. The Bizium engine was born as a testing framework for the connectors. Now is a complete runtime in which you can emit events, change events like Kafka Connect. And the Bizium server, which takes all the best from the engine and the connectors, which is our solution to do CDC. Last but not least, we have the Bizium operator, in which you can deploy, you can manage the Bizium server inside the Kubernetes cluster. And the Bizium platform, which with a friendly UI, you can create data pipelines in a very easy way. Now we have also a new component, which are the Quarkus extension for the Bizium. I think that all of you know about Quarkus. Quarkus is a Java framework. It's a Java framework for web application for microservices, which has a focus on native build, okay? Also, I mean, a lot of other features, but I mean, the main focus at the beginning of Quarkus was the native build. And well, now with you can do change data capture inside the Quarkus application. The benefits are a lot. The first thing is that you can take the best of Quarkus inside your CDC solution. As I said before, you can build in native. The Quarkus extension for the Bizium are compatible with the native build. So you can create a Quarkus application with the CDC inside, and you can have a fast startup time and a very low memory footprint. And obviously, you don't need all the infrastructure that you should have if you want to deploy the Bizium, you want to do change data capture with Kafka. Last but not least, you have some API and some friendly annotation to build and to get data from a database. Well, now, what are the use cases? Well, the same use cases that I showed you before are still valid, but the bread and butter for the extension are the pattern from monolith to microservice, like the Strangler Fig pattern. And mostly, to be more general, all the pattern in which you want to move responsibility from a system, suppose a legacy, a monolith, something that you want to move in another system, in another service. Well, CDC can help you, and the Quarkus extension is a good fit because you don't need, maybe for political reason, maybe for, I don't know, you don't like Kafka, well, you can do CDC. And for example, if you have an old system and with a data source and you want to invalidate a cache that share the data from this monolith, well, you can do it. As I don't have so much time to show you a full working example with Quarkus, I can use JBang. I don't know if someone of you know JBang. I really like JBang because it's a very light level tool to create some Java code as a scripting language and as some macro in order to add also the dependency in a very easy way. So it's the best way to showcase you a bit something. So let's jump to the demo. Okay, so can you back? Okay. Well, do you see the screen? Okay, so suppose that okay, so let's define our expectation from this demo. Okay, I don't have so much time, so I will do a very easy use case. I want to snapshot, shot, and stream change events from a database, in our case Postgres, okay, to the standard output, okay? A very easy use case. Well, in a normal scenario, you should using Kafka, you should take the Bizium connector, in this case for Postgres, deploy it in Kafka Connect, and then sync it. No, well, you should create some topic, so you should move in some topics the data and then sync. Or using the Bizum server, you can simplify the cognitive load for the application that you should deploy, but in any case, you have a unit of deployment. Suppose that you don't want to do all this stuff, but... yes, okay, I can... Okay, now it's bigger, so it's clear. So, as I said, I want to snapshot and stream this change data capture, no? Okay, so let's try with JBang. So, suppose that you have installed JBang with the SDK man, no? You can add the catalog for the Bizum. Okay, I already downloaded. And the catalog for the Bizum contain this boilerplate. Okay, suppose that I want to initialize an inventory, which is my domain. Okay, inventory. Okay, I want to initialize a project. Sorry. Okay, inventory. Okay, so you have mostly a Java application, like a Quarkus application, but with only one Java file, okay? The boilerplate contains all you need to do change data capture in a very easy way. You have the application.properties that is already configured with your local environment. A Docker Compose equipped with, in this case, a Postgres image which is CDC ready, and an initial script with fake data. Let's give a look to the fake data. We have some, some tables, customer, product, and orders, and some data, okay? In our expectation for the demo, I want to see this data, okay? So let's give a look to the inventory.java, okay? The Java code. I don't know if you are familiar with JBang, but I really like JBang because it has this macro, which simplify a lot the dependency management. So in this case, we have the boilerplate provide me the Bizum Postgres extension, the Quarkus arc, and the BOM. Here we have a class that I don't know if you are familiar with Quarkus or Spring, which is, this annotation define a stereotype in which add this class in the context of Quarkus. Now the Bizum magic. Here you see this annotation, capturing, which say, hey, take the data from the database, okay? And in our case, as I said, a very easy use case, we are logging it. But for example, if you want, let's say, you want to sync them inside an S3 bucket, you can initialize an S3 bucket, an S3 client, and then move the data. Nothing more. Sorry. Okay. So let's see. So if I run, let's see if it works. So if I run the Docker Compose, okay. So the Docker Compose with the data is up and running. So if I detach it and I want to run the JavaScript, I can do JBang. Sorry. Here, the magic. As you can see, well, in the form of the source record of Kafka source record, there are the data snapshotted, okay? The one that I showed you before in the initial script. So now if, for example, I have a simple script to add some customer, if I run a customer, okay, sorry, okay, add the customer like Giovanni Panice, with my commonhouse.dev. This is a simple script to add to make an insert into the database. You see? New data. So we have snapshotted the data, and now we are also streaming, okay? I know, it's very easy, but the time fly, I have a few times, so this is mostly what I can show you in 10 minutes.
What was your first line of Java code, which version of Java were you on?
Well, actually, the first thing I did in Java was fix a null pointer exception and a memory leak.
Excellent.
And those weren't supposed to happen. Those Java 1.0.
Excellent.
So memory leak and a null pointer exception.
Well, that leads us very neatly into your talk.
So let's begin. Do we have any questions? Not at all. We might not have time at the end. I need 3 questions.
Do we have a data race already? No?
Okay, data race. Do we have a data race? Is that your question? Do we have a data race? So this is not a data race. This is an opportunity to ask questions about Java concurrency.
What about difference between computable future and future?
Between, sorry?
Computable future and future.
Oh, that's a great question. You see, that's what we're trying to get to here. Difference, future, and completable future. Okay, excellent. Yes?
What's the first question?
What's
Start from 0, right?
So, what's better, Kotlin coroutines or Rush threads?
Excellent question. What's worse? Kotlin or Java? Okay. I want to start with a tale of vector, and Gitan really led into this, that I'm this really old, crudgy guy who's been working with Java forever. And so one of the classes that we all know is vector, and it's been around since Java 1.0, and the idea was it was designed as a thread-safe class. So, and it's thread-safe, it protects itself against us. It might still do things which are annoying, but it's protecting itself against us, right? Where's my... Yep, need to keep an eye on the time. So most of the methods are synchronized on this, so they're synchronized. But in the first version, they actually missed some places where they needed locking. So for example, this is the first version of vector, version 1.0. And you see that they've got a size method, which is final and int. It returns element count, but it's wrong. And I was talking to, I'm doing a concurrency course at IMC this week, and I was talking to somebody that I still need VMware on my machine because I need to be able to run Windows 2000 on my machine so that I can go back and take Java 1.0 and verify that this really didn't work. And trust me, this didn't work. This was broken. And what could happen is if you had a thread which would read the element, the size, and you updated the vector, you wouldn't see the change. So it's a visibility problem. So a simple bug, Java 1.0 and vector. And then in Java 1.1, this is now answering the first question about the data race, they added a race condition into the vector. Who can see the race condition? Yeah?
Size is not synchronized.
Yeah, that's not a race condition. That's a visibility problem. Where else? Where do you see a data race? So what they did in Java 1.1 is they made vector implement serializable, so that means you can actually change it whilst you're writing it. So one thread can write it, other thread can change it, you end up with corrupt data. And this stayed in Java for a while. Java 1.4, they fixed most of the problems. So they fixed, first of all, the size. So this is now synchronized, so you see the most recent value. And they also added a write object method, which is synchronized. Okay? So now all the problems are solved, and we can ship, right? However, Java 1.4 could deadlock. And quite often when we have a race condition, when we add synchronized, we actually add other problems. We add contention, we add deadlocks into our system. So you can see here I've got two vectors, v1, v2. If they each contain each other, then, and you serialize them from two different threads at the same time, you can end up with a deadlock. And I mentioned this in a newsletter many years ago, and I was like, well, this will never happen. But it actually did happen, and IBM actually coded specifically around that, right? So Java 1.7, they fixed that. So Java 7, we have now a write object method where they make a clone of the element data, and then they do the write fields outside of the synchronized block to avoid this deadlock. Okay? So brilliant, fantastic, problem solved. Java 1.8, and basically this was actually a little bit worse than the previous one, because we've got the for each method which is synchronized. So if you, from inside there, access, for example, another vector, and that accesses you and its for each, you just have to call size or anything which is synchronized, you end up with a deadlock, so quite easily. And this one is still there, so it's Java 25, it still has this potential deadlock. And there are other classes in the JDK which code specifically around this problem. So, but as you can see, a simple class like vector, which I don't know how many, 500 lines of code, if that much, has all these potential problems which just keep reappearing. So what do you learn from that? Well, first of all, thread safety is quite subtle, and obviously they've got tests. Obviously they've got acceptance tests. They've got the TCK, and still these things kept on creeping in there. And unfortunately, when it comes to concurrency bugs, you need to know what to look for in order to test it correctly. So a while ago, I started almost as a hobby to do like teardowns. You know, people buy phones and they rip them apart and they say, what speaker do they have? And how does the battery look? And they've got these videos of people, they really rip apart the phone or a laptop or something like that. I tried to do that with Java to concurrent classes. And I thought, let me do that. And I started recording very detailed teardowns where I look at like array blocking queue. And I spent 4 hours of recording on array blocking queue. And like, I sold like one copy because no one ever would want to buy that. I mean, it's like, if you've got a serious problem of insomnia, it's a perfect gift for yourself, right? Other than that, but it's a lot of fun doing this. And so I do it for my own enjoyment, actually, more than anything else. We've got a rule book that's the Java memory model, and it has all these rules about what happens before, ordering, access, safety, etc. But we can't take our class and give it to someone and say, is this correct? Are all the problems solved in this one? We run our code, we hope it works, but some bugs are very, very hard to detect. And some bugs only appear on different hardware. So, for example, here's a bug that I noticed. And apparently, at some point, there was a bug, or there is a bug, I don't know if it was or is, where if you use lock support in your class, and you don't preload that, what can happen is that the class loader could consume the unpark, and you end up with a deadlock, right? And somebody from Google managed to write a test. It took a whole week of CPU time to prove that this can happen in Java 7. And so after lots of back and forth, the recommended workaround was to force lock support to load early. And so you'll see this code all over the JDK, wherever they use lock support, you'll have a static initializer block where all they do is they load the class, they say class ensure loaded equals lock support.class, and that's it. So, but what I noticed is that they don't do this for some of the newer classes that they use for virtual threads. And I asked the question, do we still need this? And the answer was, I don't think we do, right? Because in Java 9, they use a concurrent hash map, which ensures lock support is loaded, so probably not. And quite often you'll find these bugs where we don't think this can happen anymore. They're sometimes very, very hard to prove and to find. So, and this brings us to the classes in the JDK. Most of the time, if we need to do some state-dependent classes, we can write our own. Of course, it's a lot of fun, but it's better to use something which is an existing library, which others have written, not because they're better than us, because we're very good programmers, but because more people use their code. And because more people use their code, there's a high probability that bugs that are there have been found. Okay? So by studying what's available in detail, we can learn how they work, and also we can learn how to write robust thread-safe classes. So we all make mistakes, of course, and test-driven development helps us, but it's far more difficult for concurrent code because there's so many combinations. So what we do is we try to rely mostly on well-known synchronizers rather than just picking weird classes. So for example, if I need a hash, some type of map, I'd rather take a concurrent hash map than a concurrent skip list map. I like concurrent skip list map, but how many of you use concurrent skip list map? Right, exactly. Not many. I'd prefer a link blocking queue over link blocking deck. And what I did was quite a while ago, I started reporting bugs in the JDK. And this is not all of them, but this is some of them that I found. And most of the ones that I found, I actually found whilst playing around, and most of them are in little used classes. So, for example, link transfer queue is a bug that was added. I think it's Java 22 or somewhere around there, maybe 21. I can't remember exactly when it was added, but we fixed it in Java 26. And so you'll see that these classes, and a link blocking deck hardly anybody uses. I found 5 bugs when I was looking at it in great detail. And these are like very weird bugs, from race conditions to possible problems with out-of-memory errors and all sorts of weird effects that can happen there. And basically, the way I look at it is eat your own dog food, right? If you have a class being used a lot in the JDK, then I'd be more comfortable using it than if nobody uses it. So for example, concurrent hash map is used hundreds of times, and then you've got like the copy and write array list, the concurrent link queue, concurrent link deck, future task, link blocking queue. These are well-used classes. And so if you use those, you probably are going to be okay. Further down the list, it's a bit more suspect. So try to use the most used classes, and you have a better chance of not being the person to find the bug. Because some of these bugs are very, very hard. And they'll appear once a year, and that can cause problems. Okay, so this is just a quick, I tried to position my QR code so that it doesn't overlap with the lines on the screen. And I think I got it right, but if you get that wrong, it's also tinyurl.com/amsjug26. And that is, the link works until 5 to 8. So you've got another 40 minutes to get that done. Once you get it, you've got the lifetime access to the course. But I always say try to complete it before the end of February so you can learn something from that. And so let's have a look at one of the classes, Striped 64. This is the concurrency class. And what we want to do is we want to add up numbers, have a counter. And we're going to take atomic long first of all, and we're going to take that, and here's my atomic long, 0 to 100 million. I'm going to just put a timer around that, a shortcut I wrote, and let's do that again. Call it atomic time, and let's run that, and we'll see how long it takes to run. So this is my atomic long, and all it's doing is it's incrementing a number 100 million times with 12 threads. I've got 12 threads in my system, 12 cores, so it's going to be 5 seconds for running that. Okay, so it's no warm-up, just very simple code over here, and it's 5 seconds. Okay? And then if you do the same thing, but with the Striped 64, so let's comment this out because I'm done with this demo now. Let's do the same thing with Striped 64. So we're doing 0 to 100 million in parallel, and we're incrementing the long adder. So that's the adder time. And so the one was 5 seconds. This is 124 milliseconds. So it's like 50 times faster, right? to essentially do the same thing, to add up those numbers. So that's quite a big difference. And probably if we call it a few times, it's going to get even faster, because it's not even warmed up. It's like it's not even breaking a sweat. So maybe if I run this several times, it might get down to 50 milliseconds. Quite possibly. Let's put that into method, test, and call that 20 times. And hopefully we'll speed up a bit with this one. So yeah, so you're going to about 50 milliseconds, as I suggested. So it's about it's almost 100 times faster than using atomic long. All right? So the question is, how does that work? Is that just magic? So what we want to do is we actually want to look at how the long adder stripe 64 works, just to get some idea. And we're not going to go into the nitty-gritty details, but we want to get some idea of how this thing works. So the long adder, the one thing we want to try and do is to avoid having multiple threads updating the same memory at the same time, right? So with atomic long, the way it'll work is you've got a shared field, and all the threads are trying to update that same field at the same time. So all read the value, try and update it, write it back, and some will win, some will lose the race. But for long adder, this is based on something called striped 64. And striped 64 has something called a base. Now the base is a long, and if you only have one thread, which is ever reading this base, then you will only ever have that base, and that's it. And it'll be very fast, no clashes, everything will work fine. But the moment that you've got two threads which are accessing the base, the moment you've got two, if one of the threads loses the race for updating the base, then we create an array of cells. So you go from just one, to two. Each cell is annotated as contended, which means that it's going to make it quite large, 128 bytes, so that it lives by itself in the cache line, to reduce the probability that you have multiple cells within one cache line that are unrelated but which get flushed because the one gets written, so the other one also has to get written. So, and so this is why it's so fast. You've got independent cells. If I, for example, do the following, let's go back to my demo. So what I'll do is I'll set a breakpoint over here. Now, normally when I run this, if I open up the long adder, I've just lost the long adder. I need to do it over here. Adder, long adder. So I'll set the breakpoint over here. So if I set the breakpoint here, so if I run it over here, and I get to, no, it needs to be debugged, sorry. If I open this up, you'll see I'm going to have 16 cells. It's going to be, I've got 12 cores, it's going to make up to 2 to the power of x, which is slightly bigger than 12. If I start up and I say I'm only going to have 4 processors in my machine, I say minus active processor count equals 4, then I'm going to only have, oh, again, I must put the debug on, not the run. The long adder now has an array of 4 cells, right? So it's going to be, according to the number of threads, according to the number of cores, I'm going to have that array sized, okay? So this is really, really powerful and a really great class to use. And the takeaway is the best way to deal with contention is not to have any contention, right? And if you ever want to have some fun, compare the properties class between Java 8 and Java later than 8, Java 25, for example. It's a huge difference in performance. Now, when I started, Chetan, you started this with me being so old. When I started programming in Java, it was 1997. I had one of the better machines in the company, which was a 64 megabyte desktop machine running Windows NT. 233 megahertz, 32-bit of course. My laptop here is 96 gigabytes of RAM, you know. Back in the day, memory was scarce, and so you couldn't imagine creating a collection with billions of entries. And the only types of threads we had were platform threads. We didn't have cool Kotlin coroutines or virtual threads. So there we were limited to thousands. So I've answered that question about Kotlin, right? Okay, good, excellent. I'm done with that one. So but what's interesting is that there are bugs at the limits. So for example, I figured out a way in which you could actually make a linked blocking deck that allowed you to fill it with too many items. And normally it doesn't work, but if you pass in a collection that has more than integer.max value items inside, now how do you make such a collection if you only have 96 gigabytes of memory? I made a fake collection that pretended it was that big and then returned those many values and iterated over those. So if you make one larger, then it actually had an overflow. It actually made the linked blocking deck with too many items and overflowing the size. And I fixed that for Java 26. But another one which I didn't find is that in reentrant lock, they ran out of read locks after 65,536 read locks. Now, you might say, who on earth would ever have that many threads sharing the same read lock? Hopefully nobody, right? And prior to virtual threads, this was inconceivable that you would have that many threads at all in the system, plus sharing a read lock. But it actually works it's actually quite possible to do this with Java, with virtual threads. So here what I've done, I've got a new virtual thread per task executor, 100,000 readers, and I've got a read lock, and all I'm going to do is I'm going to just keep on running, keep on going until I've gotten all of the required read locks. Now if I take Java 23, let's take Java 21, a very, very old version of Java. And I'm going to go and run that. That's the many read locks. Wait, hold on. That is the demo's many read locks. And you can see that okay, before I look at the answer, what do you think happens when you run out of read locks? Yeah, what type of problem do you see? Sorry?
They cannot take more, acquire more results.
Yeah, once you run out of 65,000, what do you see? What's the exception that comes back?
It's blocked, no?
No, it's not blocked. Out of memory error? No, not out of memory error. No, very good. But no, you actually get back Java lang error. Java lang error. Yeah. So they fixed that in Java 24, I think it was. No, Java 25. So they fixed that in Java 25. If anybody's ever crazy enough to make that many virtual threads to speak to one read lock, then you don't get Java lang error anymore. You now get your 100,000. So basically they've changed from an abstract queued synchronizer to an abstract long queued synchronizer, and the problem has gone away. Okay? So there's so many like interesting little bugs that you'll find in the JDK like this. So if you need to if you need to create something, like let's say for example I want to have a starting gun synchronizer, and what this does is basically says I want to have a service that takes some time to start, and I want everybody to wait until that service has started before starting. So, and I don't want to deal with interrupted exception. Nobody likes interrupted exception. So what I'm going to do is I'm going to have a method await uninterruptedly and a method ready, and basically my data is going to call await uninterruptedly, and once everything's set up, I call ready, and now all the waiting threads wake up without worrying about the interrupted exception. And so this is the first solution I'll just make a synchronized method. While not ready, wait, and then ready equals true, notify all. Very simple class. And wait notify is compatible with Java 25. Before that, don't use it with virtual threads. Now, another way to do this is to take the countdown latch and make a countdown latch of size 1. And then inside here, I'm going to get the interrupted status. While true, latch.await, and then break, catch it, and save it for later. And once I'm done, if I was interrupted, I'll reinterrupt myself before exiting. This is a very common way of working with interruptions. You'll see this all over the place. For example, lock.lock. There are lots of places where they do this. So we save it for later. We don't want to lose that information. Another way to do this is to say, you know, I could also just copy what countdown latch does. And there actually are very few classes in the JDK that you can just copy and paste. Because most of them have got some like legalese on there. But countdown latch is in the public domain, which is quite interesting. What I can do is I can go to the countdown latch, and I can, that's the wrong one. Countdown latch, and it says here at the top, it says somewhere public domain. This was written by the team of this available under, yeah, it's a public domain, this one. I'm not sure this one is, yeah. Okay, so I can take this code, I can copy and paste it, and I can just adopt it for what I need. So it's basically going to be the contents of this class, copied and pasted, and I can use the same approach to make my starting gun. So it's going to be similar to the countdown latch with these two methods inside here. So it's going to be also a sync. The sync is going to be an abstract queued synchronizer. The count is just going to be 1, as opposed to the countdown latch has any number of count. I don't need this count. And then try acquire shared and try reshared, just leave them like they are. And then we're going to need our, this you can leave out because that's already set. Oh, we need to just say equals new sync. And then await, we don't need, we're going to have await uninterruptedly. So let's look for where the await method is. Await, and it's going to be basically, instead of saying await acquire shared interruptedly, it's going to just be acquire shared. And then the other method we have is the countdown. This is going to be release shared at the top, and basically that's it. We're done. Just need to delete some things that I need, like this code that I need. There's a whole bunch of stuff that I need. I can delete basically the rest of this, I think. So let's just delete the rest. I think the rest is not necessary. So I've got now a starting gun, which is based on the countdown latch, almost exactly the same, except that this one doesn't have. Don't worry about the interrupted exception, and it's only for 1. So then, just to make sure that it actually works, I'm going to just run my test because I just hacked this together quickly. So let's run the test, make sure that it works. I hope it works. And it does. Okay, so my little copy and pasted code actually does complete the way that I wanted it to work. Now, which one is the best approach? Well, the thing is that the synchronized wait is not fully compatible, so I'm not too happy with that. And the problem with copying and pasting countdown latch into my own code is, what if there was actually a bug in countdown latch? Now, I've also copied and pasted the bug. We don't want to do that. So even though I think that the one based on the countdown latch is more work, I think it's a better solution because I'm reusing what's there. I'm reusing the countdown latch. If there's a bug and they fix the bug, I get the fix for free. But if I copy and paste the code, I'm also copying and pasting the bug as well. I think this should be quite clear. All right. There's an interesting class called linked blocking queue. And it's interesting because they do something called lock splitting. What lock splitting does, it's a single data structure with multiple locks. So I can put something into the link blocking queue at the same time as I can take something out of the link blocking queue at the same time. So now comes my question. How many of you have used the link blocking queue? Okay, one person, 2 people, 3 people. Not many people. All right. How many people have used a fixed thread pool? All right. The fixed thread pool uses a link blocking queue. So if you use a fixed thread pool, you've also used a link blocking queue. Okay? And it's interesting because they try to have 2 locks, one for put, one for take. And this gives you a better throughput for the single producer, single consumer case. But you can get surprises if you've got multiple consumers. All right, so let me show you a quick demo on that one. And where's the demo? There's, oopsie, that was wrong. There. All right, so what I've got here is I've got a link blocking queue. And then what I do is I'm going to have one thread that puts elements into that queue, and I'm going to have a number of consumers at the moment 1 that takes elements out of the queue. And so what I'll do is and we'll test it 10 times, where I'm putting elements in and taking elements out. So it's 1 in, 1 out. And we can see that as we run it, it's about 800 milliseconds or so to put the elements in and take them out again. Okay? So nothing too complicated, just 1 thread in, 1 thread out. Now, let's try the link blocking deck. That's double-ended queue. This does not do lock splitting. It has a single lock for put and take. So now we're competing on the locks. And you can see it's a little bit slower than the link blocking queue because you've got contention on the lock. So for the case where you've got 1 and 1, the link blocking queue is better. All right? Let's take another one, the link transfer queue. Oh, no, sorry, the array blocking queue. This also has a single lock for put and take. And again, we see that it is a little bit worse than the link blocking queue. All right? Do you all agree? Smoke and mirrors. This is all smoke and mirrors. All right, now let's go back, and we're going to go back to the link blocking queue, and we're going to have 2 consumers, each getting half the elements, and 1 thread putting elements in. So this is now 2 consumers. And we see that the link blocking queue is sometimes actually quite good, and sometimes not so great. So there's sometimes where it's like 1.5 seconds, then it goes faster, then it's bad again. So sometimes it's good, sometimes not so great. And the times where it's really bad is typically when you've got GC happening at the same time. So what's happening is I'm putting elements in really quickly, but I'm not. And the queue can get quite long this way. Let's do the link blocking deck, which was slower. And look at that. That's consistently faster. Okay. So it's a single lock for putting and for taking. And the array blocking queue, let's try that as well. Also, much better. So what's happening is when you've got a link blocking queue, there's 1 lock at the front, 1 at the back, 2 different ones. But what's happening is that when I put, the putting, when I'm putting with 1 thread and I'm taking with 2 threads. So the putting is uncontended, but the taking is contended. So the taking is throttled, and so the queue is getting longer and longer. That's when it gets slow. End up the GC is going to cost you more, and as a result, it ends up being quite a bit slower. Okay, some nice surprises. So what I've often seen people do, they would make these demos where they would take very small jobs and they'd give it to a single-threaded fixed thread pool. And they'd say, okay, so this does 10 million jobs per second, right? And then they'd give it to one with 2 threads, and they'd say, but this only does 3 million jobs per second. And the reason is that if you have 2 threads in a fixed thread pool, it's exactly that case, where you've got 2 threads competing for the take, and 1 thread putting elements on. And so you end up with the problem there. All right. There's also some other weird things, like, for example, the array blocking queue. It's a circular array list, and they actually have weakly consistent iteration, but in addition to that, they want to keep track of iterators which are still in play, so that they can notify the iterators when you loop around the array. So what they actually do, they've got weakly consistent iteration, but they also have weak references pointing to the iterators which are in play. It's the only place in Java where they've got that. So it's kind of weird. I mean, actually, the queues shouldn't be iterable. Also shouldn't have a size method. And then lastly, quite fun, I just want to show you one piece of code. So you've got this copy and write array list. I spent far too much time looking at that. And what they try to do, if you remove an element, remember it's copy and write, so they don't want to actually make the copy unless it's necessary to make the copy. So remove would be at least an order n cost, because you first have to see, does the element exist in there? And if it does exist in there, then they call remove, and that's when they actually do the synchronized. So initially, they don't do any synchronization. They look, does the index actually appear in there? So I want to show you what that looks like, because it's quite funny. I think you will agree. Where's my... This one here. So here's remove, and you go to the remove, and there you can see the most beautiful code. If snapshot not equal to concurrent, they've got a label on the if statement, right? And you go like, why would they do a label on the if statement? I mean, we've probably seen labels on for loops, for continue, but they even have a label on the if statement. Now, whenever you see this type of code in the JDK, don't just dismiss it as being bad code. It's not that great, but there's usually a reason why they do this. So don't be too quick to dismiss it. All right, so if you're not on my newsletter, you should be on there. Geert-Jan's been on there for like 35 years or something. But yeah, so join that if you want, javaspecialist.eu. It's the longest running Java newsletter in the world, as far as I know. It's even longer than FoodJ's newsletter, almost, or just a bit longer. The second longest is Jack Shirazi. He started 3 weeks after me. And if I ever stop 3 weeks later, he'll be the longest running Java newsletter in the world.
It's a highly selective, invitation-only, super secret conference, except out in Rio. But just talk to John or to Heinz if you want a top secret ticket to an awesome, invitation-only, super limited conference.
You know what? One of the best, the funniest was. We were invited to JFocus, which is, I think, honestly, one of the best conferences in the world. Really, really good. And not just did they pay for my trip there, they even invited me and everybody on a ski holiday, right? And so we went skiing, and they had dinner for free. It was just unbelievable, like just so cool. And we were sitting there having dinner, and Geert-Jan says, "Hey, do you guys know what the best Java conference in the world is?" And I'm going like, "No, don't do this, don't do this."
Sitting opposite the guy who founded JFocus.
And I said, "Don't do it." I said, "Don't do this, don't. Geert-Jan, rein yourself in." And he says, "J Crete." And I said, "Come on, don't do this to me."
Anyway, are there any questions or comments before we go into the break to Heinz on this topic?
Difference between future and completable future. Future is just a return value that you get from when you submit a job to a thread pool. Okay? And you can use it to cancel. But completable future is a way in which you can build up basically an abstract syntax tree of your concurrent process. So if you've got a very complex activity diagram, you can take that, convert to two completable futures, and then nest everything together. And there's an interesting change that happened in Java 25, which I discovered this week, that in the past, if you had a single core or dual core machine, and you used completable future, it would make a new thread for every single async request. It would just make unlimited number of threads. And they did this because you can also start up the common pool with 0 threads. But they changed that in Java 25, that if you've got 0 threads inside your common pool, and you do an async completable future, they actually put 2 threads into the common pool. So that you don't have this problem anymore of an unlimited thread creation of completable future. So they've become a lot more usable than they were before. Okay? Any other questions?
Shall we take a break unless there are questions? Thank you. Thank you very much.
Thank you.
Hey everyone, thanks for joining me today. And today I just want to walk you through our experience from migrating from Maven to Bazel as build systems. So a bit about me beforehand. My name is Talha. I graduated from university in August 2023 and ended up joining IMC as part of the Global Developer Productivity team. Our team pretty much owns most of the software development lifecycle. And our goal here is to provide modern tooling and resources for our devs, allowing them to focus on delivering high-quality solutions in a confident and tested manner. We're a group of 10 engineers now, spread across 3 different offices, Amsterdam, Chicago, and Sydney. Our team has a couple of different domains. For example, the local and remote development environments, IDEs, build tooling and CI/CD, as well as more recently the GenAI tooling landscape too. Outside of IMC, I also participate a bit in open source, mainly around developer tooling in the Lua ecosystem. Before I dive into our migration, I just wanted to talk a little bit about build systems. Who here, I'm guessing, has heard of Maven before or used it? A good portion of you. What about Bazel? Okay, a fair amount of people. But I just wanted to give a brief overview to get people up to speed. But first, what really is a build system? When you first start out with Java, maybe you ended up using the Java-C compiler to get started, compiling a couple of different source files together to produce some class files, which you can then load into the JVM. As your project begins to expand in scope, maybe you write a shell script or maybe even a makefile to automate parts of this and keep it repeatable. As your project continues to scale, these shell scripts or makefiles probably don't scale with it. And that's where a build system might come in to help out. And a build system really is a tool to automate converting that source code into executable binaries or libraries, but also manage the various different tasks that might involve. Maybe that's compilation or code generation from tools like Protobuf or Avro, handling both internal and external dependencies, as well as packaging the final result for something that you're able to deploy. And so Maven. Maven is probably one of the most widely used build systems for Java. We can call it a task-based build system. Here, you're writing your build out in an XML file, like a POM file. And this build definition defines a set of tasks that we want to execute for our build. These tasks execute at different stages of something called a Maven lifecycle, such as the generate sources or compiles or testing. Some of these tasks might have dependencies on each other too. Many of these tasks are provided by Maven, such as via the Maven compiler plugin, but some can be provided by external plugins too. And these plugins, they can just pretty much execute any Java code. Here's an example of a build file definition you might see in Maven. This one's a little bit more complex. In your POM file, you'll probably define a bit of metadata about your build, the group ID, the artifact ID, and maybe some dependencies that your module might rely upon. Module here is just like a set of related Java files. In this case, our module also defines a custom plugin that we want to run during execution, in this case during the generate sources phase. This Maven CodeGen plugin, it ends up taking some input from a CodeGen directory and then just generates some code somewhere. Most likely it generates it out into the target directory for Maven. But this plugin here has full flexibility to execute anything. Maybe it goes out to the network to get some information. Maybe it writes some files into a particular directory, just as an intermediary or as a result. This gives a lot of power to the build engineer or whoever's writing these plugins and defining the build. But giving that power to the plugin limits what the build system might be able to do as well. You might end up having issues when you're trying to parallelize multiple plugins executing at the same time, if they depend on conflicting resources. Similarly, you can't really guarantee that running this plugin again is going to produce the same thing for the same inputs. So then you struggle with incrementality sometimes. Then we get to a build system called Bazel. Bazel is a different paradigm. Here we can say it's an artifact-based build system. Instead of defining the series of tasks that we want to execute, we just define what we want to build, the targets we want to build. We go from that imperative approach to a more declarative approach. And the reason being is we're giving more power back to the build system. In Bazel, you define your builds in this language called Starlark. Starlark is kind of like a Python dialect, which has a couple of tweaks to support better determinism and hermeticity. And these two concepts, determinism and hermeticity, are a lot of what Bazel relies upon. You pay a bit of cost to try and set up your build in a way to support these ideas. Determinism, where given the same set of inputs, we always produce the same outputs. Hermeticity, where we only rely on the inputs we've been given and don't rely on anything else or anything from the host system. But paying the costs to support this allows Bazel to develop fast and correct builds, and incremental builds and distributed builds as well across multiple machines. With Maven, you get a base set of defaults. You follow the Maven standard, you pretty much get a build for free. But with Bazel, you have to pay the cost a bit to structure your build in a certain format, but then you unlock these benefits. Here's an example definition of a Java library in Bazel. We've defined our sources as inputs, as well as some dependencies, some other Bazel targets we might rely upon. And the Java library rule explicitly has an output underneath, under the hood. The mylib will end up generating a jar that we can later consume. So Bazel translates this Java library definition into a fixed set of actions. These actions, again, have inputs and outputs, and multiple different actions form together to make an action graph. And with this graph, Bazel is responsible for scheduling and executing those actions. But it now has control about how and when they're going to get executed. So a bit about build systems. Now let's talk about the problem that we had. At IMC, we have two main repositories that form our execution system. One is a C++ repository that we call Roadrunner. This monorepo was already migrated to Bazel. And alongside this, we had a second repo containing a lot of our Java controller code. We called it Skippy, or trading internally. And this repo was what was on Maven. But these two repos are pretty connected to each other. The end result that we deploy into production was a combination of both C++ binaries as well as the Java controller system. And if, as a developer, you're trying to make a change to the C++ or the Java, and a change to both of them, on average, it would take you 22 hours to get a release out with your changes that you could later use for testing in an environment. Similarly, if you're because these repos are so connected, they have a protocol in between. But if you make a breaking change to that protocol, which was a fairly common occurrence, now you had to go through all the pain of trying to manage that release and dependency bump that happens internally between the two. So at this point, at around February 2024, we decided it was time to merge these two repos together. and we plan on migrating from Maven to Bazel for the Java part. So the build migration. First, we had to map out the landscape. Our Maven repo contained over 450 different Maven modules, housing over 6 million lines of code here. And this Maven build had around 50 different kinds of Maven plugins. Each of those had various different configurations scattered around the place on different modules too. And we also had to understand the CI/CD structure, how this build is being used to release something. And there were over 100 different CI builds we had that were making use of this repo. And before we begin migrating, we had to make a decision about how we were going to roll out this migration and how we were going to make those build.bazel files. With around 240 active contributors to the repo, we decided it was important to work out of band and behind the scenes, where we tried to minimize the disruption as much as we can to our developers and delay the enforcement of breaking the Bazel build until as late as possible when we were comfortable that it was in a state that was usable. We wanted to also minimize the transition cost for devs, allowing them to follow in a similar mindset to the way they may have been working with their Maven build. And for making the build files, we decided about this idea of module level granularity, where we'd convert one Maven module to one Bazel package. And to go a bit deeper into that, the granularity of our single target definition could vary. And we went for the left-hand side approach, where in your Maven module, you might have some related source files in a source main Java directory with a couple of different packages. And we'd create a build.bazel that would mimic that too. However, you could go a bit more fine-grained. Maybe we could generate a build.bazel for each individual package in this module instead. Group xy.java together and a and b.java together. And the value of potentially going fine-grained would be that we'd have faster distributed builds and less need to rebuild targets. Let's assume that x and y and a and b are like independent of each other. And if we made a change to x.java, if we were more fine-grained, we wouldn't need to recompile a.java or b.java. And this also applies to executing tests as well. So that's a granularity option we could have chosen with Bazel. But also, you could also break down your Maven build as well to have a bit more fine-grained approach. But we went with the left option. And the reason being was because of our build file generation. The way we decided to go about it is we wanted to automate the most part of generating that Bazel build. And we did this by getting the output details from Maven by generating an effective POM. In the POM XML file that you have committed to your source code, it's probably not as descriptive or it doesn't contain all the tasks that are actually getting executed. That's because a lot of those tasks are coming from inherited parent POMs. But the effective POM allows us to join all these together into a single XML file. And we could take that XML file and use that to generate a build.bazel file. Our generator would register various different handlers that would take a particular part of that POM XML and then create or modify the Bazel equivalent. And that one-to-one mapping between the Maven modules to the Bazel modules is what allowed this easy build file generation, because we could just follow the same method with that POM file. And then granularization, that would involve probably reading source code within our build file generator on a more complex solution. But granularization is probably something we could proceed with later. So we have a build file generator. We run it on our repo, and we end up getting a Bazel build graph. We might even find that some of those Bazel targets already start to compile, probably because the target was just a vanilla Java code with maybe no dependencies or maybe just internal dependencies. But after that point, we needed to figure out where to start, where to go next. Given the scale of our repo and that the build was constantly changing as well, we needed to figure out where exactly we should spend time to work on plugins in order to unlock parts of the compilation. Bazel has a nice introspection function, the Bazel query, to dissect and understand parts of your build graph. This particular command is what we can use to generate a visual graph of what our Bazel build might look like. So we decided to run it. And what did we get? So our Maven build and our Bazel build was not that great. Everything was just scattered around everywhere, and our graph is just difficult to parse. We struggled to find various different visualizers to actually show the graph. And then we ended up finding one which showed something like this. But this was not particularly useful to figure out where to go from next. This is a direct acyclic graph. So we could do a little bit more simplification here. We decided to group together related nodes or related targets. So this really just meant modules which are similar in nature and might be near each other in the build graph. And also perform a function called a transitive reduction, where we just remove unnecessary edges, but still keep the reachability definition intact. Where if two nodes are reachable to each other beforehand, they'll still be reachable afterwards, after we reduce edges. That ended up giving something like this, still difficult to read, but maybe a bit more manageable. Then we decided to add a bit of color to it as well. So each node here is a build target. If we color build targets which already compile as green, and then targets which don't compile, but all their dependencies do compile, if we color those as yellow, we end up with something like this. And those yellow parts there, those are action areas that we should probably tackle next. And if we tackle those, we'd probably be able to unlock a larger portion of our graph and continue onwards. So this graph visualization was a key enabler to help us scope the problem out better, and also to just visualize the progress of our migration. So we know what target to tackle, then what kind of stuff do we need to tackle? One of this is probably code generation. From our experience, what we saw is that most Maven plugins were really code generation plugins. And there are two ways we could tackle that. First is to find a CLI tool that does what the Maven plugin was kind of doing, normally provided by the project that we have, like Avro tools or Swagger CodeGen. But if we didn't have a CLI tool, or if it didn't meet the requirements that we had, then we could end up just creating a new Java main class that was relying on the same libraries that the Maven plugin was using, but we can use it to inject it into Bazel. But it's important that our code generation follows those Bazel principles outlined earlier. We needed to have predefined inputs and outputs. And these paths were given upfront by Bazel and had to go in. It was also important that our code generation enforces deterministic outputs. Given the same inputs, we're always generating the same thing out. And also that it works in the Bazel sandbox. If we need something, we should make sure it's being declared as an input so that it shows up in the sandbox. And this is what helps to ensure that our actions are self-contained. Here is what a Bazel rule might look like in Starlock. This is a rule for Avro. And the key thing is the context actions run, which is registering an action that we execute in the Bazel's action graph. Here we're taking Avro tools CLI as an input, as an executable, as well as the source files as input. And then we're outputting it into a directory. We have to do a little bit of magic for Bazel here, where we output files into a directory. We don't know what those files are going to be beforehand, but we output it into a directory, and then we need to zip them together into something that's called a source jar, and so that we have a single jar that Bazel can then take onwards. So alongside code generation, there's also the question about third-party dependency management. Bazel itself doesn't have built-in mechanism for Maven dependency management. If you were going to go for the pure Bazel approach, you'd have to find all your transitive dependencies up front and then list them out as archives to pull in. And then that would just be a bit of a pain. But there is a popular open source rule set out there called Rules JVM External, which helps to resolve and fetch those Maven artifacts. So it works by you defining all of your third-party dependencies for the repo upfront, and then it will asynchronously ahead of time use that to compute a transitive lock file. This lock file is what Bazel actually takes in during a build to generate targets that it can reference. And the way that Maven and Bazel process dependencies is quite different. In Maven, dependency versions are resolved per module. And you might have heard of the idea of nearest definition wins, where if you've got a transitive dependency coming from a couple of different dependencies, then the one which is defined closer in the POM file is the one which we go for. And this transitive resolution is quite implicit. Bazel, on the other hand, you define those versions up front, it computes all the transitive dependencies up front, but you have to have one version and apply that across your whole repository. And there's quite a challenge here on that version alignment as well. Then there's also Java testing. If you look at the built-in Java test rule in Bazel, it's actually quite limited. That's because you can only define a single test class as an input for a single Java test rule. And that doesn't really work for a Maven module which has tens or hundreds of different Java test files. So you can build a bit of scaffolding around this to make it work better. We have two options. One is to write something called a Bazel macro, which ends up generating multiple Java test targets, one for every single test source file, and create a separate target there. Or there's a second option. We're using JUnit4 here, and we can use something called a suite class in JUnit4, and we generate that suite class upfront. It will statically list the test classes we're going to run, and if those test classes show up on the class path, then it will execute fine, and now we have a single entry point. Both of these options have their trade-offs. A single Java test rule will run in its own JVM and also has to pay the cost of setting up the sandbox. So if we go for that former approach, we're going to have to pay quite a bit of cost for a lot of targets to set it up. In the latter approach, though, where we have a single Java test, so we're running all these tests in a single JVM, then if these tests are non-hermetic, which is something we found was the case in a lot of our Java tests, where if they're setting up state, if they're failing to clean up global state, or if they're relying on test cases, previous test cases executing that configured certain states that they wanted to test against, then they would fail due to a different ordering or structure in Bazel. This normally happened when we're having singleton classes in use or some sort of static initialization. Another case of flakiness we saw in Bazel was now we could execute a lot more Java tests in parallel, and we'd end up with a bit of resource exhaustion. One example is network resources. Some of our tests relied on locking ports for a certain communication. Fortunately, in Bazel's case, Bazel gives us a network sandbox we can use for each individual Java test. So that means each test would run in its own network namespace and then would not have those port collisions. So we started the build migration February 2024, and in 3 to 4 months, around May time, that's where we're at a stage where most of our Bazel build compiles, and pretty much all of our Bazel build compiles, and pretty much all of the tests are passing. Now it was time to make it more available and roll it out and test what it would look like in production. Before we go straight to production, we spent a lot of time looking into static validation of what our outputs were. Could we compare the outputs between Maven and Bazel and make sure that we're catching any issues up front? A couple of examples here is like comparing the jar structure. The file layouts should pretty much stay the same, and the generated code as well. Bytecode was a bit difficult to match here because Bazel was using a different compiler to what we were using in Maven. Then going on from there, we spent some time looking at the class path and analyzing whether it's set up correctly. Flagging potentially duplicate class names showing up on the class path as they would cause a problem later. And also spending some time looking at reachability analysis. From our main entry point for our executable, could we look at all the symbols that we're statically referencing and making sure those are still available on the class path. Finally, as well, just comparing the JUnit XML outputs between Maven and Bazel, as our testing should have matched. One example of the class path issue. You might have heard of SLF for J before. It's what we call a logging facade, or just a general way to define logging in your Java source code, but allowing you to configure at runtime how those log messages are processed. You can have different logging backends, like log4j or logback classic. And in our repo, we actually had two different logging backends used at the same time. One was logback classic, and another was an internal logging backend that was passing those log messages into our monitoring systems. And it was very important that the logging backend we used, there's only a single one on the class path. They shouldn't mix together, and we should be using the right logging backend, particularly in that internal case, otherwise our monitoring would not work correctly. In our Maven build, we saw that it was actually exploiting exclusions to kind of mitigate or ignore this problem. Exclusions is something you can define in your POM file, where you kind of just remove a transitive dependency from the class path and just say that you don't really need it anymore. Bazel, you can have third-party exclusions, but exclusions within the repo, which is what we were also seeing, is not something which really works or makes sense in Bazel. And that required us to rethink and develop a bit of a more robust approach here. That involved really just breaking up these targets into smaller parts with an application target and a library target. And other targets within a graph should only be relying on the library target. They shouldn't be taking in that application code. And that application target is the one which should define the logging backend it cares about. So after all this static validation and initial testing in the test environment, we ended up with our global production rollout. All of our execution systems at IMC had to make that switch between Maven to Bazel. And that required coordination between various different offices to make that switch possible. But that ended up happening with fairly minimal issues. And then, so here's the timeline. Kickoff in February. By May, the raw Bazel build itself was working. In September, we ended up merging the two Git repositories together and making some CI changes. And this is where developers started to actually see the build in practice. October and November, that's where we spent a lot of the time at that static validation and also responding to potential developer feedback as well about the build. December, January, we kicked off that production rollout. And by March 2025, that was when we were able to remove Maven and join those two build graphs together. So, the results. In our CI, we were able to see a 4x speed up in just the CI times for the Java build. That's compiling and also running those unit tests. Maven, this was taking P50 20 minutes, but for Bazel, we got that down to 5 minutes. There wasn't really a difference in the actual compilation time that Maven and Bazel were seeing. They were pretty comparable, but it was really the more faster, the more parallel test execution that Bazel enabled to cut down that time. And also this other idea of dynamic CI. With Bazel, because of the declaring of the inputs and outputs, and if you have a change to a source file, you can figure out exactly which downstream targets are impacted by that change. And then we could filter down our graph. Rather than running every single unit test in the repo, we only run the unit tests which really matter. Maven and other tools, they can provide a similar option, but in Bazel, we could guarantee its correctness. Alongside this, we saw that our CI machine hours cut down by half per week. On the release side of things, when we're looking at just the Java part, releasing a Java-based change, we got it from P50 1 hour 12 minutes down to 34 minutes. Again, via that better parallelism and also just restructuring and figuring out how our build setup would work in the new landscape. Similarly, we saw a significant improvement to our success rates for the Java pipeline as well. In our Maven build, we were seeing, on average, a 50% weekly failure rate for our Maven pipeline for a variety of different reasons, such as the flakiness. But given spending the time deeply looking into that flakiness and making it work better with Bazel, we were able to get that to below 15% failure rate. So for developers themselves, the biggest improvement here was the idea of atomic commits. So now that the repo is all together, you making that breaking protocol change, you can make that all in one go. You don't really need to babysit those changes across an internal dependency bump, getting various different release pipelines out, green, and ready to go. Similarly, the incremental build improvements were Bazel. It doesn't really need that Bazel clean that you might need in Maven. It's able to track correctly exactly what needs to change and what needs to rebuild. And our DevProd team, on our original Bazel monorepo, we spent a lot of investment in build tooling and infrastructure. And now our Java repo was able to get all of that for free. Things like remote caching and remote execution for the build. That idea about dynamic CI earlier. And other things like metrics and monitoring, as well as flaky test management. But for us, the biggest outcome for developers was cutting that 22 hours down to less than 6 hours for getting a release out from that contained both C++ and Java changes in your commit. Our release pipeline runs every 3 hours in this case. And what this kind of means is that you submit a change in the morning and you can already go and start testing in a pilot environment or even getting it out into production by the next day. Of course, Bazel isn't a silver bullet, and there are trade-offs here. As you might have seen, Bazel has minimal batteries included, and you need to spend the time into developing your Bazel scaffolding, be it through custom rules and macros, or even just the way that your project or your company defines the writing build files. So user education upskilling is required here. Everyone needs to learn a new build tool, but even more than that, less familiar developers with the build system, it's harder for them to try and understand and make complex changes to the build. Whereas if we were in with Maven or maybe Gradle, it's a bit more straightforward, a bit more standard, and it's used outside of IMC quite a lot as well. So you'd have those external resources too. The one version enforcement we saw for third-party dependencies is something we had to consider greatly. You've got more of a risk now in making a dependency upgrade. Now you're impacting every single project in the monorepo. Here, test coverage is very important to consider. Also, the idea of maybe automated dependency bumps or automated dependency upgrades to try and reduce the amount of big bang changes we're making in one go. We don't want to be upgrading 2 or 3 years worth of changes. And also the IDE integration is a common question that people say with Bazel. From what we've seen, the IDE ended up working fairly well with our Bazel and Java build. Of course, IntelliJ's integration is not as mature as what Maven would be. And you end up having some road bumps, some bugs here and there. Some cases we had where generated code was not getting picked up correctly. But we do see this continue to improve. And the problems we have there are solvable. It just requires digging deeper into the IDE integration and the way it understands the Bazel build. So this is our journey and a quick tour of how we migrated from Maven to Bazel. Hopefully you were able to learn something here. But thank you for listening and happy to take questions. So in our case, we don't cache flaky tests. If the flaky test is failing, we will repeat the test. But I agree with you that just a raw switch from Maven to Bazel isn't really going to make that number change. But it was more the investment into understanding our tests and running the tests, for example, understanding the non-hermeticity in our tests, running tests which in separate JVMs help to solve a bit of that flakiness. And just that investment there is what mainly made that success rate go down. Bazel does have a couple of other options, like, for example, if a test is flaky, you can retry a test 3 or 5 times. You pay the cost, but if a build is green, maybe that's good enough for developers. So there are a couple of extra things that you can use there as well. Yeah. So for dependency management, I think the main issue is alignment between different third-party dependencies. So say, I don't know, it's a bad example, but let's just say JUnit. There was some tests which rely on JUnit 4. Some dependencies rely on JUnit 4.11 and 4.12. JUnit's a very bad example because you wouldn't want tests dependencies on your compile time, but for sake of example, then if you have code changes in 4.12 which are not present in 4.11 but a dependency is relying upon it, then that's where the risk kind of comes in. In Maven, you might be able to just scope that down to a particular module. Okay, we'll accept this increase in version there. But for Bazel, we have to apply it to the whole repo. And the idea about like dependency management, I don't think it fully applies. Well, in Bazel, you're already basically creating a dependency management section for your whole repo already. And you can't really section it down into smaller parts. Yes, yeah. So indeed, I think in the majority of cases, you have a single dependency tree for your repo, but you can indeed have multiple different dependency trees if it makes sense for your repo. But it's very important that those dependency trees never mix. So if you say have dependencies which are specific to Android or dependencies specific to general Java, and you don't ever want intermixing between the two, but you can partition it in such a way. But if you had a generic library, you'd have to maybe I'm not so sure, but maybe duplicate that generic library definition twice, once for each kind of class path. Out of the box, I don't think so. Indeed, we also wrote our own solution to do something similar to this. When we were in that stage where we had merged the repos, but the C++ or the Roadrunner side, which also had a bit of Java code, and the new Java controller Skippy side were in the same repo, but with different dependency trees, we had an approach to make sure that these were separate via a mechanism called Bazel aspects. Yes, exactly. Yeah, where we just prevent that collisions. And I haven't seen anything built into Bazel for that. We are in a transition phase between Bazel mod and workspaces and trying to get to Bazel mod.
Thank you.
Okay. Yeah. Any other questions directly to Tana in the networking afterwards? Thank you so much. Clearly a lot of interest in this topic.
Cool. Thank you.
Thank you very much, Tana.